When I play this out, you can see that we get a similar kind of graph. The only difference is that this time the position represented by x stays constant at 50, whereas erstwhile it remained constant at 0. Let's try one more time, and this time I will drag the car to the 100, let's say the negative 50 mark, and I will play it out, and we will see that the relation between the position of the car and the time is such that the position does not get affected by time at all, and that is why the position remains fixed at whichever position we place it at the start of the time of observation. Let's plot this behavior on Desmos. Such a behavior in which one property of nature, in this case f represents the position and t represents whatever this function depends upon, is just a constant. This function shows that the position, and I may be able to plot it with p, the position p of the car, which was dependent on time, or which we expected to change with time, did not change at all and was always at one constant value. And that is why this equation is one of the simplest equation possible, that the position of the car, which was supposedly dependent upon time, was not really dependent on it at all. And that is why throughout the passage of time that we observed, the body remained at 50, because that is where we left it. Then there could be slightly more sophisticated graphs, and let's take a look at that. Let's just say that this blue dot was our previously observed car which was at rest, and now we have another car, that is the red car, and we will see the behaviors of both just in terms of how they physically behave, just by looking at this simulation. Okay, so I'll play it out, and you'll see that the red car moves at a certain pace, and it seems like it covers equal intervals of length in equal intervals of time, whereas the blue dot stays stationary. We are already aware of the blue dot's graph, position versus time graph, and that is a horizontal line. But what should we expect the graph of the red car, which is moving at a certain constant speed, which is not changing, and it can be seen from the fact that at every instant of time it covered the same distance, which means there was no such instant in which the car sped up to cover more distance or slowed down to cover less distance. Let's reset it, and this time watch the animation with the graphs. We are already aware of the blue graph because the position is not changing with respect to time, whereas the red one shows a straight line still, but this straight line is not completely horizontal, it has some slope. The physical meaning of this red line could be that every second some activity was happening on the y-axis. Some position change was being registered, and we can see that after 8 seconds of observation of the red body, it had changed its position from 0 meters to 40 meters. We could say that the red body covers 40 meters in 8 seconds, and if the same trend continues, then we could predict that in 16 seconds, which is double of 8 seconds, it would have covered double the distance. So for every 8 seconds it covers 40 meters. For the next 8 seconds it has covered another 40, which has made the distance 80 now. So a slightly more sophisticated behavior is this red line, and let's plot it on Desmos. So I will also call this the position graph. So I'm going to hide the previous one. This is the position of the car which is dependent on time, but in this case it is dependent on time in some way. You can see that I added this extra k to it, and this k is a number, and instead of adding any random number like 2 or half to it, I am putting a knob there, and name of that knob is k, and I can turn the knob so that there would be a different number placed according to the value that the slider will take. So this number right now 2.4 is what this equation is carrying in the place of k right now. Could we adjust this graph in such a way that it would give us this relation? We would need to adjust this graph in such a way that for every 8 seconds this car covers 40 meters. Can we do that? Let's try. Let's zoom in. We want this car to cover 40 meters for every 8 seconds. This should be 8 seconds, right? And right now this graph says that in 8 seconds this behavior has covered, this body, whatever it is, has covered 4 meters. Well, if we raise this, so you see that if we keep raising it, then for these 8 seconds the distance would keep increasing, and if we keep increasing this to, let's say, 4 or just 4, you would see that above this 8, if I go above exactly this 8, I would find that so far this body is covering 32 meters in 8 seconds, which is still not the case that we want. We want it to cover 40 meters at 8 seconds. And now that you can see that if I go on top of this 8, the tiny 8 that you can see that exactly 40 meters have been covered. So we have replicated the behavior of the red dot that we saw on the other tab, and you can see that our behavior went from the simplest behavior of a constant number to a constant number being multiplied with the independent variable in this context, which is time. Now there are several other behaviors that could be possible, and we will take a look at them in just a little while.